All right, get ready because we're going to see a deep dive into some really cutting-edge AI research today.
Sounds good.
We are talking nGPT, a new architecture that is, it's making a lot of noise.
Yeah.
Because it can potentially train transformers 4 to 20 times faster.
Wow.
That's right. You heard that correctly.
That's impressive.
4 to 20 times faster.
Wow.
For AI engineers and researchers like you, this is, well, a potential game changer, to say the least.
It really is, yeah.
So let's jump right in. This deep dive is based on a research paper from NVIDIA. It's called nGPT, Normalized Transformer with Representation Learning on the Hypersphere.
Oh, okay.
And it's a pretty dense paper, really technical, packed with details
Yeah.
that are going to be super insightful, especially for those of you, who are working at the cutting edge of AI.
Yeah, definitely.
So the foundation of nGPT is in this innovative use of hyperspheres.
Oh, okay.
Now, this is where things get really interesting.
All right.
Imagine a hypersphere, a multidimensional sphere.
Okay.
nGPT maps all vectors, including embeddings, MLPs, tension matrices, hidden states. All of that is mapped onto this hyperspherical surface.
So the paper states it really clearly, and I'll quote it here. In nGPT, all vectors forming the embeddings, MLP, attention matrices, and hidden states are unit normalized.
Okay.
Basically, every token in the input stream is represented as a point on this hypersphere.
Interesting.
And as that token goes through the model, its representation moves across the surface of this hypersphere.
Okay, so picture this, okay?
Yeah.
Each token is like a tiny spaceship,
Okay.
navigating a vast cosmic map, which is our hypersphere.
I like that.
And each layer of the model acts like a course correction, guiding the spaceship toward its final destination, which is the prediction of the next token.
That's a great analogy. I like that a lot. The paper actually uses a similar visualization, stating that the input stream of tokens travels on the surface of a hypersphere, with each layer contributing a displacement towards the target output predictions.
There you go. So we have this fascinating concept of representing everything on a hypersphere.
Mm-hmm.
But why is this such a big deal? What does it actually do for us?
Well, the big benefit, and it's a big one, is faster convergence.
Okay.
The authors highlight this right from the start, and I'll quote, "Faster convergence. We demonstrate that the normalized transformer reduces the number of training steps required to achieve the same accuracy by a factor of 4 to 20.
4 to 20 times faster. That's an incredible speed increase.
It is.
And it's not just in specific cases.
Right.
The paper emphasizes that this faster convergence is, it happens across different context lengths, model sizes, and even downstream tasks.
That's right.
Think about what this means.
Yeah.
We could train these complex models in a fraction of the time that it currently takes.
Yeah.
And use way fewer resources.
Think about how this could really open up AI research, make it accessible to smaller teams.
Absolutely.
Maybe organizations that have limited, computing power.
Democratize it.
Yeah, exactly.
Well, and then also accelerate the development of new AI-powered applications, getting them to market much faster.
Absolutely. It's exciting to think about.
So how does nGPT pull this off? What are the changes, the modifications that make this possible?
There are several key changes. First, they completely eliminate normalization layers, things like layer norm and RMS norm.
Okay.
And the paper is very direct about this, saying, remove all normalization layers, such as RMS norm or layer norm.
This seems a little counterintuitive at first, right?
Yeah.
I mean, normalization layers are usually used to stabilize training and make things run better.
That's true in traditional transformers,
Right.
but in nGPT, the hypersphere representation kind of provides its own inherent normalization.
Right.
By mapping all those vectors to the surface of the hypersphere, they all have the same magnitude.
Okay.
You don't need explicit normalization layers anymore.
Interesting. So what happens next?
So after every training step, nGPT normalizes all the matrices, including embeddings. You've got your WQ, your WK, WV, and so on. And the paper says, after each training step, normalize all matrices, input, output, WQ, WK, WV, WOW, and WARMELI, along their embedding dimension.
Right. Nice.
So this keeps all the vectors on that hypersphere, maintains that normalized representation during the entire training process.
Okay, that makes sense. But how do they actually handle updates on the hypersphere? I mean, moving a point across a curved surface like that must require some special techniques, right?
Yeah, you're right. Initially, they thought about using what's called spherical linear interpolation, or SLIRP,
Slurp.
to make sure the updates were smooth on that hypersphere.
Okay.
And the paper explains SLIRP like this. For any points A and B on the surface of a hypersphere in ARD model, SLIRP, spherical linear interpolation, but Shoemake, 1985, computes an interpolation along the geodesic shortest path.
So Slurpee calculates the shortest path between 2 points on the hypersphere.
Exactly.
This is pretty logical.
Yeah, totally. But when they ran their experiments, they found something really interesting.
Huh?
They realized they could actually approximate solar effectively with a much simpler method called linear interpolation, or LRP.
LRP.
And they state, our experiment suggests that Celer can be approximated by simple linear interpolation, LRP.
It's got to be good for efficiency, right?
It is, definitely. A simpler method without sacrificing performance is always a win.
Absolutely.
And it shows how dedicated they are to optimizing and streamlining everything. They're always looking for ways to improve efficiency without compromising the effectiveness of the model.
So we've covered the hypersphere representation, getting rid of normalization layers, normalizing the matrices, and then the simplification from slurp to lerp. Anything else?
Well, now we get to one of the most interesting parts of nGPT, and that is the introduction of what they call eigenlearning rates.
Eigenlearning rates.
Yeah.
Sounds complicated.
It's where things get really exciting, I think. So the paper introduces them this way. We denote Fella as eigenlearning rates, from the German word eigen, meaning own, referring to the internal structure of the transformer.
Okay.
Essentially, these eigenlearning rates, they act like individual control knobs for different dimensions within the model.
So instead of just one learning rate that applies to everything, nGPT gives each dimension its own unique learning rate.
Exactly.
Huh.
It's like giving the model a deeper level of self-awareness, allowing it to adjust its learning strategy as it goes.
That's amazing.
Right. These eigenlearning rates make nGPT much more dynamic and responsive during training, which could lead to faster convergence and better performance overall.
Okay, so we've got the hypersphere concept, no more normalization layers, normalization of the matrices using LERP, and then now these eigenlearning rates. It's a lot to keep track of.
It is.
But before we dig into how all of these pieces fit together, let's take a step back and ask, how does nGPT actually perform? Does it live up to all the hype?
The results are pretty impressive. nGPT shows significantly faster training convergence compared to the traditional GPT models.
Okay.
I mean, we're talking about hitting the same performance level in a fraction of the training steps.
Wow.
And this is clearly shown in Figure 1 of the paper.
Yeah, Figure 1 shows a huge difference in those validation loss curves.
Right.
nGPT just dives down towards its best performance much faster than GPT.
Exactly. And this faster convergence isn't just a fluke. It's consistent across different model sizes, different context lengths, even those downstream tasks.
Yeah.
And Figure 2 really shows this off. It showcases how nGPT consistently beats GPT across the board.
So it's not just training faster, it's also getting better results with fewer resources.
Exactly.
That's a big win for efficiency.
Absolutely. And this efficiency translates into better performance on downstream tasks, too.
Okay.
Figure 3 shows that nGPT gets higher accuracy on those tasks compared to GPT when they have the same computational budget.
So nGPT isn't just some theoretical thing, it has real practical applications.
Definitely. And the paper goes beyond just showing better performance. It actually digs into some really interesting analyses that help explain why nGPT is so effective.
Let's hear about those.
Okay, so one of the biggest things they noticed is the difference in what are called embedding norms between nGPT and GPT. Figure 4 shows that GPT has a much wider range of these embedding norms,
Okay.
while nGPT keeps a fixed norm for all embeddings, which makes sense, right? Because it's mapping everything to that hypersphere.
Right, they all have to have the same magnitude.
Exactly. And the paper argues that this more controlled distribution of embedding norms is part of why nGPT creates a more stable and what we call well-conditioned learning space.
So by keeping those embedding norms in check, nGPT creates a more predictable learning environment, and that can explain why it converges faster.
That's what they think. And there's more evidence for this idea.
Okay.
The paper looks at what are called the condition numbers of the attention matrices in both nGPT and GPT. And Figure 5 shows that GPT's attention matrices tend to have much higher condition numbers.
Now, for those who might not be familiar with condition numbers, what are those?
Good question. They essentially measure how sensitive a matrix is to changes in its input.
Right.
A higher condition number means it's more sensitive, which can make it less stable, less reliable during training.
I see.
And the paper argues that nGPT's normalization procedures, especially that normalization of matrices after each training step, helps to address this issue, leading to attention matrices with better conditioning.
So by keeping those attention matrices well-conditioned, nGPT makes sure they're more robust during training, and that contributes to its overall stability and performance.
Exactly. And this brings us back to those eigenlearning rates.
Yeah, tell me more about those individual controls for each dimension. It's fascinating.
I know, right? So figure 6 shows how these eigenlearning rates actually change during training. And you can see that nGPT learns to take these measured steps in the direction suggested by the attention and MLP blocks.
So it's not just blindly following the gradients, it's choosing its updates more strategically.
Exactly. And this suggests that it's developing a more nuanced understanding of how different components within the model are actually contributing to the learning process.
It's like it's figuring out which parts are most important for learning at any given time.
Right. And to take this even further, the paper highlights a key observation. The average magnitude of these eigenlearning rates is different between the attention and MLP blocks,
Okay, meaning,
meaning different parts of the model need different learning rates.
so the attention mechanism might need more fine-grained adjustments compared to the MLB block.
Exactly. And this difference could be because of how complex each operation is. The attention mechanism, with its focus on relationships between tokens, might just need a more delicate touch than the MLP block.
So it's not just about having individual learning rates, it's about understanding how those rates should be different based on what each part of the model is doing.
Precisely. And this nuanced approach to learning is one of the things that makes nGPT so effective.
This is all incredibly fascinating. I mean, we've seen how nGPT uses that hypersphere concept, introduces these innovative things like eigenlearning rates, and achieves these impressive performance gains.
Yeah.
But I'm curious to know more about how it's actually implemented.
Okay.
How do they actually change the attention and MLP blocks to work within this framework?
That's a great question.
It is.
And that's exactly what we're going to get into in the next part of our deep dive.
Stay tuned, folks. We're about to go even deeper into nGPT. We'll be back soon with part 2.
Can't wait. Welcome back to our deep dive into nGPT. So, like we promised, we're going to really get into the nuts and bolts of how nGPT changes those attention and MLP blocks. You know, the real workhorses of that transformer architecture.
Okay, let's start with the attention block.
Yep.
That's where the model figures out, like, the most important parts of the input sequence, right?
Exactly. In a traditional transformer, the attention mechanism works by calculating the dot product between what are called queries, keys, and values. And then these dot products get scaled down by a factor of, well, 1 over the square root of the key dimension.
Right, and that scaling factor is there to kind of balance out the variance in those dot products so they don't get too big.
Exactly. But remember, in nGPT, everything is normalized to have that unit norm.
Right.
All those vectors, including the queries, keys, and values, they all lie on the surface of our hypersphere.
Okay.
So the paper suggests changing the scaling factor.
Oh.
Instead of 1 over the square root of the key dimension, nGPT uses the square root of the key dimension.
Huh. That's an interesting switch. Why the change?
The paper explains it pretty well. They argue that, and I'll quote, in the original transformer, the softmax scaling factor 1, AIR-D, in equation 13, is introduced to account for the expected variance of dk in the dot product of non-normalized query and key vectors. In the normalized transformer, the expected variance of the dot product between normalized query and key vectors is 1 dk. To restore a variance of 1, the softmax scaling factor should instead be SIC.
So because nGPT already normalizes the vectors, they had to adjust that scaling factor to maintain the right variance.
Right. It's all about making sure that attention mechanism works within the limits of that hypersphere representation.
That makes sense. Now, besides the scaling factor, are there any other changes to the attention mechanism?
Yeah, nGPT does another interesting thing. They normalize those query, key, value, and output matrices along their embedding dimension before they calculate the dot products. This keeps all those vectors on the hypersphere, reinforcing that normalized representation.
Right, keeping that normalization consistent throughout.
Exactly. And this normalization has a subtle but important consequence.
What's that?
The dot products between the queries and keys, which are now normalized vectors, can actually be seen as something called cosine similarities.
Cosine similarity.
Yeah.
Refresh my memory. What does that mean again?
So cosine similarity measures how alike two vectors are in terms of their direction. It basically calculates the cosine of the angle between them. A cosine similarity of 1 means they're pointing in the same direction.
Right.
And a similarity of 0 means they're orthogonal, totally different directions.
Right. I remember now. So nGPT's attention mechanism is basically calculating the cosine similarity between those query and key vectors. Why is that a big deal?
It means that the attention scores, which tell us how much each value vector contributes to the final output, are now limited to between -1 and 1.
Okay.
This keeps those attention weights stable and well-behaved.
Ah, I see. Another way to make sure everything runs smoothly within that hypersphere framework.
Exactly. And to control those query and key vectors even more, nGPT introduces more scaling factors. They use psych to represent these.
Secret.
Yep, these are trainable parameters that adjust the impact of each dimension in that dot product calculation.
So they're giving the model even more fine-grained control over our attention.
Exactly. The paper gives the equation for these scaling factors. It says, we introduce scaling factors as in equations 15 and 16, where SLIKE is treated with Iowa and ACTK Scale 1 Iowis model.
Okay, so that's how nGPT changes the attention block. What about the MLP block? That's the part that does the nonlinear transformations, right?
That's right. The MLP block usually has two linear layers with a nonlinear activation function between them.
Okay.
And in traditional transformers, the input to that MLP block is often normalized using something like a layer norm.
Right. But nGPT gets rid of those extra normalization layers.
Exactly. So instead of normalizing the input, nGPT focuses on scaling those intermediate vectors that are produced by those linear projections within the MLP block. They use scaling factors, SU and SGOF, to control how much these intermediate vectors contribute to the final output of the MLP block.
Okay, I'm following so far, but why scale those intermediate vectors? What's the point of that?
The paper explains this in detail. They say that scaling those vectors helps to really make the most of that nonlinear activation function, which is usually SIU, sigmoid linear unit, in nGPT. And they explain that we propose to normalize matrices WU and WV along the embedding dimension so that the U and V vectors represent the cosine similarity between HN vectors stored in WU and WV, respectively. To control their impact, we introduce scaling factors, SU-ROD MLP and SV-ROD MLP.
So by scaling those vectors, they're basically adjusting the strength of those nonlinear effects from the SIU function.
Exactly. And this fine-grained control over the nonlinearity lets nGPT find more subtle patterns in the data.
Interesting. It's like they're giving the model more tools to work with.
That's a great way to put it. And this emphasis on nonlinearity is really important for deep learning models. It's what lets them learn complex relationships and make those sophisticated predictions.
So we've seen how nGPT changes both the attention and the MLP blocks. But what about optimizing the learning rate? Traditionally, transformers use things like Atom W, which has weight decay built in. Does nGPT do the same?
Actually, no. nGPT uses the standard atom optimizer without weight decay.
Really? Why the change? Isn't weight decay supposed to be important for preventing overfitting?
It is in traditional transformers.
Right.
But nGPT argues that its built-in normalization, especially that step where it normalizes matrices after each training step, already acts as a kind of regularization.
So by keeping those vectors on the hypersphere, they're preventing the weights from getting too large without needing explicit weight decay.
Exactly. That built-in regularization makes the extra weight decay unnecessary.
Clever simplification. It streamlines the optimization without losing those benefits of regularization.
Exactly. And there's another interesting tweak they make to the learning rate optimization.
What's that?
nGPT gets rid of that learning rate warm-up phase that's common in transformer training.
You mean where the learning rate slowly increases at the beginning of training?
Right. That warm-up phase is usually there to stabilize training in the early stages.
Okay.
But nGPT says its normalized architecture already makes things stable, so they don't need the warm-up.
So they're simplifying things even further by getting rid of a step that's usually considered essential.
Exactly. And this shows a pattern with nGPT. They're always looking for efficiency and elegance. They're trying to streamline the model and how it's trained without sacrificing performance.
Like they're refining it, getting rid of unnecessary complexity, and revealing the core of what makes the transformer work.
That's a great way to put it. And this focus on simplicity and efficiency is one of the most appealing things about nGPT.
Okay, we've covered a lot of technical details here.
We have.
But let's take a step back and look at the bigger picture. What are the big takeaways? What does this research tell us?
One of the biggest takeaways is that we can actually think of nGPT as a kind of variable metric optimizer.
What does that mean?
It means it's not just updating its parameters based on those gradients, it's actually learning how to learn more effectively.
It's like it's becoming self-aware.
Exactly. And the paper says it directly. In other words, the normalized transformer functions as a variable metric optimizer, searching for output solutions using data-driven gradient information estimated in its attention and MLP blocks.
So nGPT isn't just a fixed architecture. It's actually a dynamic system that's always evolving.
Exactly. And this opens up some really exciting new research directions.
Like what?
Like, it suggests that we could design AI models that are not only powerful, but also really adaptable, able to change their learning strategies depending on the task or the data.
That could change everything about AI.
It could. We could have models that are more robust, more efficient, and ultimately more intelligent.
This has been a really insightful look into how nGPT works. We've seen how it reimagines those attention and MLP blocks, streamlines the optimization process, and gets those impressive performance gains.
And in the next part of our depth dive, we'll go through the paper's performance evaluations, looking at the evidence that supports nGPT's claims. We'll also look at some of those interesting ablation studies that shed light on the importance of different design choices they made.
So stay tuned, folks. We're about to see the proof behind nGPT's success. Welcome back for the final part of our deep dive into nGPT. We've talked about a lot, exploring its core concepts, unique modifications, and what it could all mean.
Yeah, it's been a deep dive for sure.
But we're not quite done yet. The paper goes really deep into evaluating how well nGPT performs.
Right.
And the results, well, they're exciting, to say the least, especially for all you AI engineers and researchers out there.
I think they'll be impressed.
So one of the biggest findings, like we've mentioned before, is how much faster the training is.
Yeah, that speed boost is impressive.
The paper says nGPT achieves faster convergence. They actually say, we demonstrate that the normalized transformer reduces the number of training steps required to achieve the same accuracy by a factor of 4 to 20.
4 to 20 times faster? We're not talking about a small improvement here.
It's potentially a huge reduction in training time.
Huge.
And the paper backs this up with solid evidence. They show the speed up in Figure 1. You can see how quickly nGPT gets to the same performance level as a traditional GPT model, but with way fewer training steps.
Just a big difference.
This faster convergence, I mean, has massive practical implications, right?
Oh, yeah, absolutely. Think of all the time and resources you could save. Researchers could try out different models much faster, experiment with bigger, more complex architectures, even get those AI-powered applications out there in the market quicker.
And it's not just about speed, right?
No.
The paper also shows that nGPT actually performs better on those downstream tasks.
That's right. You can see it in Figure 3 of the paper. Given the same computational budget, nGPT consistently outperforms GPT across a range of different tasks.
So it's not just faster, it's actually better.
Better and faster.
That's a pretty powerful combination.
It is. And this better performance comes from, at least partly, nGPT's unique approach to representation learning. Remember, everything in nGPT is mapped onto that hypersphere.
Right.
This leads to some interesting differences compared to those traditional transformers. You can see it in the paper's analysis.
You're talking about the analysis of embedding norms and those condition numbers, right?
Exactly. Figure 4 shows that GPT has a much wider range of those embedding norms than nGPT does. That's because nGPT normalizes everything to have that unit norm, keeping those vectors on the surface of the hypersphere.
Right. So while GPT's norms can jump around during training, nGPTs stay nicely controlled.
Exactly. And this control seems to contribute to a more stable and what we call well-conditioned learning space. The paper suggests that the stability is a big reason why nGPT converges faster and generalizes better.
Okay, that makes sense. And then there's the analysis of those condition numbers, which we talked about earlier.
Right. Figure 5 shows that GPT's attention matrices tend to have much higher condition numbers than those in nGPT.
And just to remind everyone, a high condition number can mean that a matrix is really sensitive to changes in its input, which can make it less stable during training.
Exactly. And the paper says that nGPT's normalization steps, especially that normalization of the matrices after each training step, helps to keep those condition numbers under control. This gives you more robust and reliable attention matrices.
So nGPT isn't just about speed, it's about stability and robustness too. It's like it creates a more controlled and predictable environment for learning.
Exactly. And this focus on stability and control carries over to how nGPT handles learning rates. Remember those eigenlearning rates we talked about? Those individual controls for each dimension?
Oh yeah, those are fascinating.
Well, Figure 6 gives us some really cool insights into how those eigenlearning rates actually behave during training. It shows that nGPT learns to take these measured steps, following the directions suggested by the attention and MLP blocks.
So it's not just following the gradients blindly.
No, it's more strategic with its updates.
It's like it's becoming more aware of its own learning process.
That's a great way to think about it. And the paper dives even deeper, looking at the specifics of those eigenlearning rates. They noticed that the average size of these learning rates is actually different between the attention and MLP blocks.
So different parts of the model need different learning rates.
Right. It makes sense if you think about it. The attention mechanism might need more fine-grained adjustments compared to that MLP block.
Okay, and why would that be?
It could be because of how complex each operation is. The attention mechanism, because it focuses on relationships between tokens, might need a more delicate touch than the MLP block, which just does more straightforward transformations.
So it's not just about having separate learning rates, it's about figuring out how those rates should be different depending on what each part of the model is doing.
Precisely. And this nuanced way of handling learning is a big part of why nGPT is so effective. But the paper doesn't stop there.
Oh.
They did what are called ablation studies.
What are those?
They're basically controlled experiments. They take out or change specific parts of nGPT to see how it affects performance.
So it's like figuring out which parts are really important.
Exactly. And the findings are pretty interesting. One of the ablation studies looks at those scaling factors we discussed earlier.
The ones that control the influence of different vectors within the model.
Right. We talked about SWINK, SU, and SE.
Right.
They tried out different ways of initializing and using these scaling factors, and the results, which you can see in Table 4 of the appendix, show that the default settings are generally pretty robust.
So the standard way of handling those scaling factors works well.
It does, but there might be room for some tweaking and optimization.
Okay. What else did they try?
They also tried simplifying those scaling factors, either by making them single learnable values or even just fixed constants. The results, which you can see in Table 5, suggest that these simplifications often don't hurt performance much at all.
So nGPT is pretty flexible. You can make these simplifications without losing much accuracy.
Exactly. It really shows how strong the underlying architecture is. It suggests that those core principles of nGPT are solid and can be implemented in different ways.
What about the normalization steps? Are those essential for nGPT to work well?
The paper looked into this too. They did an ablation study specifically on the normalization of those query and key vectors, what they call QK normalization.
Right, that step takes a lot of computation, so it would be great if you could skip it.
Well, they took out QK normalization, and it did hurt performance a little bit, but the drop in performance was comparable to the time saved in each step.
So it's a trade-off.
Yeah.
You get a bit of speed if you skip QK normalization, but you might lose a bit of accuracy.
Exactly. It really depends on what you need for your specific application and what kind of computing power you have available.
Makes sense. It's good to have that flexibility. Now, the paper also does this really deep analysis of those scaling parameters. It's pretty detailed, but it gives us some great insights into how nGPT actually adjusts its learning strategy depending on what the data looks like.
Yeah, they go deep on that. They looked at how those parameters are distributed under different conditions, like different context lengths, model sizes, learning rates, and how many tokens are used in training. The patterns they found give us clues about how nGPT changes its behavior depending on what it's seeing.
So what kind of patterns did they find?
For example, they saw that those eigenlearning rates, AA and M, tend to shift higher as the context length or the number of training tokens increases. Meaning the model needs to adjust its attention and MLP blocks more when it's dealing with more complex inputs.
It's like it's becoming more sensitive, more aware of the little details in the data as it sees more of it.
That's a good way to put it. And they noticed that that scaling factor, the one that controls the query and key vectors and the attention mechanism, stays pretty much the same across different situations.
Interesting.
This might mean that using a fixed value for squall, kind of like that softmax scaling factor in the traditional transformers, might be a good approach.
Something to explore.
Definitely. And when they looked at the other scaling factors in SV, they found that how they're distributed changes based on things like context length, model size, and number of training tokens.
So nGPT is actually learning to adjust the nonlinearity of that MLP block based on the data it's given.
Exactly. It's adapting and optimizing how it processes things depending on the challenges it faces.
Fascinating. Anything else?
One more thing. They saw that the scaling factor that controls the temperature of that softmax function in the final output layer tends to have higher average values when you have longer context lengths, bigger model sizes, and more training tokens.
Okay, so what does that tell us?
It might be that as the model processes more and more data and gets better at making predictions, it starts to sharpen that final word distribution. focusing more on the most likely outcomes.
It's like it's becoming more confident, more sure of its answers as it learns.
That's a good way to put it. And all of this analysis of those scaling parameters gives us a really valuable peek into how nGPT works. It shows how good the model is at adjusting itself and fine-tuning its learning strategy based on the data it sees.
It's pretty impressive how adaptable it is.
It is. This deep dive into nGPT has been really insightful. We've looked at how it uses hyperspheres in this innovative way, its unique changes to those attention and MLT blocks, how it simplifies the optimization process, and those impressive performance gains.
We've also dug deep into those analyses that show how nGPT can actually change its learning strategy based on the data.
And it's clear that nGPT is not just another small step forward for AI. It could be a real game changer, a new way of thinking about how we design and train these large language models.
It pushes the boundaries of what we understand about representation learning, optimization, and maybe even the nature of intelligence itself.
Big questions.
As we wrap up this deep dive, I encourage all of you listening, our fellow AI enthusiasts, to really dig into nGPT.
Yeah, get your hands dirty.
Explore the paper, play around with the code, and see what you can do with this exciting new architecture. The future of AI is full of possibilities, and nGPT is a great example of what we can achieve when we challenge the old ways of thinking and come up with new ideas.
Couldn't agree more.
So keep learning, keep exploring, and keep pushing the boundaries of what AI can do.
And until next time, keep diving deep.